one of my favorite things just to teach, and it's definitely one of my favorite things to like work on. And so for me, I don't need to know like why, because I just love it, right? It's like, why do you want to watch a Marvel movie? It's just fun, right? But I think for a lot of you, it's like, why am I learning this totally random crap? So I need to do a better job of explaining like the why in addition to the what and the how. Okay, so we're going to talk about stacks today, and then we're going to talk about queues later. And so I want to start with the why, so I don't forget it, and also it's kind of where we should start, is like a lot of problems in the world. When I say problems, I don't mean like hunger and like anti-Semitism from our president. I mean like like, hey, I would like to park all of these cars, in a nice little line in the way, or I would like to lock up this bicycle in a way that it can't get stolen, right? It's like a problem that can be solved, but there's this particular technique to it, right? Like the way you lock your bicycle is like, don't just lock the wheel to the wall. You're gonna pop the quick release, gone, right? So that's not a good solution to that problem. You understand? So a lot of problems are solved with stacks because there's a significant number of problems that have this what's called a LIFO characteristic to them. LIFO stands for last in, first out. So let's just think for now of an example of like, what is something in the world that is last in, first out? So I'll start with an example which is like a stack of papers. If I put a bunch of papers in a stack, right, a bunch of like homework assignments in a stack, the last one that's in is going to be the first one I'm going to take off, just the one on top. Right? What's another example of something in the world that's last in, first out?
Passengers boarding a plane.
Passengers boarding a plane. That's a great example, right? You want the people in the back to come in first, and you want the people in the front to come in last, and you want the people that came in last to leave first, right? The people that are in the front row, although the reality is that people in the front row are first class and they board first, which is stupid. That's dumb. It would be a better world if airplanes were boarded back to front and then deboarded or whatever, front to back, right? So that's a great example. What's another one? Let's think of another one. Just shout them out.
Crowded elevator.
What's up?
Crowded elevator.
That's a great example. Crowded elevator. Love it, right? You're not. If you get in last, you're not going to push everybody to get out first, right? You got to wait your turn. It's a great example. I love it. Let's think of another one.
Juice.
Juice?
Or in the cup. Have to go in the
Hell yeah. Let's go. We've got some very thick juice in that cup. It's not swirling around, but I like it. I mean, the idea is the right idea, right? So I love it. It's a good example. What else? A vending machine, exactly, right? Somebody that puts it in, they're going to put in the thing in the back first. It would be really annoying to put the stuff in the front first and then try and reach around and put it in the back, right? So you put it in the back first. But obviously, when you buy something, the thing in the front's going to come out, vending machine. So there's a lot of problems in the world that are last in, first out. So hopefully that gives you the why. Okay, thanks. You're welcome, Rena. Or thank you, Rena, for giving me that feedback. Anyways, that's why we're going to learn stacks, because we're trying to solve problems like this. Right, and we saw there are all kinds of things. So like boarding an airplane or an elevator, or like juice, or like working on a vending machine. Like there's all of these different things that have kind of nothing to do with each other that happen to have this same characteristic, and that's why stacks are so powerful. And we'll have a very similar conversation for queues in a little bit. Okay, so the goal is to understand what it is, what last in, first out means, and what kinds of problems are last in, first out, what the methods on a stack are, and how to implement it. Okay. So this example is things that you would stack. You stack pancakes, right? You stack books. You stack money. When we say a stack, we mean a stack. The implementation you'll see is obviously doesn't look like a stack of plates, but the idea is that it is a stack of plates or a stack of whatever, a stack of chairs, right? You can see that we have a stack of chair situation going on in the back right now. Or a stack of computers, or a stack of names in a database, or a stack of tasks to do, There's a lot of things that could be, like they don't need to necessarily be physical objects, right? Because oftentimes in programming we're dealing with ideas, right? Like a stack of birthdays, right? Okay, so there are two fundamental concepts with a stack. You can add a new element, And, spoiler alert, you can remove an element. End of list. Okay? So I think what's really important here, and I think A, one of the reasons why I love data structure algorithms, and B, one of the things that I think makes them deceptively complicated is their like inherent simplicity of, wow, it only has two operations, add or remove, and you can't add to the middle, you can't add to the bottom, you can't add anywhere, you must add to the top, right? I don't know if you've ever stacked plates before, but you can definitely like squeeze a plate in, right? You can do that. But a stack is made in programming so that it restricts you to say, don't do that, don't lift the plates up and try and sneak one in there, then you'd be violating the rules of the stack. You can only add it to the top, and you can only remove from the top. That's it. Following me so far? Okay, so there's one additional method that we didn't talk about, peek. What do you think peek does? Who wants to guess? What does peek do?
It allows you to check what's in the stack.
Okay, what's in the stack? So if I have a stack of names, right? I have a stack in JavaScript of names, and I call peek on it. What do you think it's going to return?
Just the name of each stack.
It's going to it's one stack with many names in it. So when we say each stack, that implies there's many stacks.
Like section.
Each name. So you think peek is going to return the whole stack? No, we're shaking our heads in front. Why do we disagree?
I guess because we're just focusing on like the last one name. It's only going to show you that you're peeking at that list and you're only going to see that last one.
Can you speak up so everybody can hear you?
So because we're talking about a stack and we're focusing on the last one in, first one out, when you're peeking, you're gonna see that last item that was put in that list.
Right, exactly. So a stack, when you peek a stack, does not give you the whole stack. If you wanted the whole stack, you probably should use an array or something that isn't a stack. Because a stack is saying, hey, you can't see the plates below. Imagine if you have a lot of plates like in your house, and maybe you have a kid, and I don't know, when I was a kid, I would like do these cool plates where I would like draw a cool thing, and then my mom would like animate it, and then it would be a plate with like my drawing on it. And I would have a stack of these plates. Now you can't see the middle plate, what's on it. You'd have to like take them off and look, right? And like that's not a good thing. Imagine if you have a really tall stack. It's really hard to do that. So like that's the same thing with a computer science stack, is that you can push to the top, you can pop from the top, and you can peek at the top. So when you peek, it gives you one element, the top element. Popping and peeking return the same thing. If you peek first then pop. If you pop first then peek, do they return the same element? No? Why not?
Maybe because you pop the first element out, and it's on one of theirs, and you peek through the next element.
Did everybody hear that? Speak up.
When you pop an element out, it's gone, and now you're left with the element that was under it. So when you peek, you're only going to see that element.
Right. So peeking shows you what's on top. If you remove the thing that's on top, something new is on top now. Right? So peeking and popping are going to return the thing on the top. Sure, they are. But popping removes it. So if you do that and if you pop first, peek is going to show you something new. Does that make sense? So that's not like a trick or whatever. That's just like part of understanding the question.
You put it like, we have to peek first before the pop. Yeah.
You don't have to do anything. You know what I mean? You don't even ever have to pop ever. This, no one's, it's a free country. Barely, but we're doing our best, or at least I am. So not everybody. Yeah, you don't have to do anything. I'm just saying that this is just a fun question, like to get it or understand it. You can peek first, then pop. You can pop first, then peek. You can never peek. You can never pop. You can do whatever you want, right? But what does it mean to peek? What does it mean to pop? Right? And what it means to pop is to remove the top element and return it. What it means to peek is just look at the top element, but don't remove it. So if you peek 100 times in a row, you should see the same thing, right? But if you peek and then pop, peek and pop, peek and pop, every peek will be different. Make sense? Okay, cool. So So we literally say the top and the bottom of the stack, and we were using these words, these English words, because the person that came up with this idea came up with it because they're trying to solve like human problems, right? They came up with this abstraction because they're like, wow, I notice there's a lot of things in the world that are last in, first out. So I'm going to make a thing that's last in, first out, and I'm going to call it top and bottom so that I as a human understand. So these names are arbitrary, but they're really helpful. Okay, so there's only two operations, push and pop, and then also peek, obviously. That's sort of an operation, but it doesn't affect the stack. It's limited access, we talked about that. Right, if you pull out a disk in the middle, it will become crashing. Okay. So, okay, here's some really cool examples. We talked a lot, we did some examples at first, right? We did the elevator and things like that. But here's a really good one. Back and forward on your web browser. Right, that's a stack. You can't like go just like a million back. I mean, you actually can because your web browser has this like, you can hold it down and you can do that. But that's a new innovation that Chrome invented. Back when I was a kid, you could just go back one at a time, right? So you're just popping off the stack, going back to previous URLs. And what was really cool about the way forward worked is that you pop off the back stack, and you take that element and you push it on the forward stack, right? So you basically pop, push. And then you'd have two stacks that would be like the pages that you were at before and the pages that you came from. Rather, the pages that you would go back to, and the pages that you went back from. Anyway, whatever. Okay, reversing a word is a stack would be a great way to do that, right? Because if I had a word, ben, and I could push B, and I push E, and I push N. Then when I pop 3 times, I'm going to get N, E, B, which is now right backwards. So it's like a really straightforward way to reverse a word. It's a good way to do things like undo. Every operation that you might do in a text editor, you could push it to a stack. When someone undoes, you just pop. Syntax checking for compilers, that's pretty complicated. Let's skip that example. Memory allocation uses stacks at the architecture level. So this is a really amazingly awesome, mind-blowing thing that I'm not going to spend too much time on because it's kind of complicated. But fundamentally, we've talked about, didn't I use a stack with you guys, you all? When we were talking about functions, right? So that's not memory allocation, but it's very similar, right? Where it's like when you're actually the actual program executing functions, a function calls a function calls a function. That's a stack, right? Because when a function returns, where does the code go back to? It goes to the caller, right? The caller was the next one on the stack. So it's exactly what we talked about last time when we did recursion. I don't remember. So that's pretty cool. Memory for local variables managed using a stack, so that's actually the same as the recursive. Basically, each stack frame has those variables on it. Anyway, okay. So here we added a fourth method, isn't. Not all stacks have that. Some stacks have a length method, which you can use to implement isEmpty, right? Length equals 0 is the way to do isEmpty. But they always have push, they always have pop, and they often have peek, and they might have length in isEmpty. Okay, any questions before I move on to the implementation? Do we understand why we might want to use a stack? Yeah? Okay. So, there are two ways of implementing a stack. One is the traditional hard way, and the other is the easier way using arrays. So, we're going to do the easier way using arrays eventually, but I think we're going to start with the array. So, check it out. We made a class. It's called stack. Can you read that? Should I read it? It's easy to read, hopefully. We make a class. It's a stack. When it gets constructed as empty, and it has an array inside it. Make sense? An array is a really good data structure for this because just like a stack, an array can grow and shrink. And an array can do everything a stack can do, but more, right? I can add and remove to the top, to the end of an array. But I can also add and remove to the front of an array, and I can add and remove to the middle of an array. But a stack can only add and remove to the top, or let's say the end of the array, or the front. It kind of doesn't matter. It's really up to the implementation. We'll see in a sec. This implementation did it to the front or the back. I think to the back, for sure. But an array, it feels like a really good solution here because it does everything that we want a stack to do. And so what we need to do is we need to hide some of the features of an array from the user so they can't just insert anything in the middle, right? We want them only able to insert at the top and move from the top. So, push. Why don't we, here, let's do the thing that I said I was going to do. Why doesn't everybody, obviously the answers are here, but maybe don't look at them, and talk amongst your partners and maybe write down in Visual Studio Code or Atom or whatever you use, write down how you would implement this. Let's take 5 minutes and everybody try and implement a stack. Go. Do it. If you don't get it, that's fine. Raise your hand. Ask your neighbor.
So basically, we have the flash right there. So how can we make it push? So, we had to do it, we had to add it. Yeah, so how do we use that? Here. So search for push, right? And then if this array is already there, then we can just do this array. Yeah. So whatever it is. Value this because I know that you have to push something, put something in there. So that it will be you gotta return it. Can't forget that. That was a stupid pressure system. Little things, right? I had it around, so I was just like, I need to see it to see if it works. So I changed it, returned it, and returned it back, and just submitted it as possible. Wow. No wonder it stopped working.
Does everybody have an answer?
Hopefully.
Is anybody still working on it? Is anybody not working on it? Is there anybody that likes to raise their hand at all? Raise your hand if you don't like raising your hand. Big surprise. Okay. Alright, so let's look at the answer for push, okay? So, oh my god, big surprise. Guess what push does? It just pushes on the array, that's it. Right? Oh my god, what does push do? I don't even remember. Let's look it up. Array push. Right? Holy shit. Where does it go? Banana, orange, apple, mango. Where does it go? Let's see. Goes to the end. Goes to the end, right? This is really the end of the array. So, hey, my spoiler was to the right. Okay, so you just push to the right, that's it. So it's like, you might ask, wait a minute, this is just an array. And you would be totally right. A huge part of these data structures, they're deceptively simple. But a huge part of this data structure is framing the programmer experience, what's called the abstraction for the programmer, around the problem. And oftentimes what that means is giving you all the same tools you had before, but actually removing some features. Right? It's like, think about it. Like if you were driving a car, if you had like a dial that was like, that would control like how much anti-lock brakes it would use, and how much electricity the spark plug should use, and how much at what level the fluids goes below should it alert you. If you can control those dials, would that make you like a better driver? No, actually, you'd probably fuck it up. You'd probably do it wrong, and then your car wouldn't work, and you'd be like, oh shit. But instead, the car's like, dude, we're not gonna let you touch the spark plug, right? The spark plug is just gonna do its thing, and it's gonna start the engine every time until it breaks. And that's an example of abstraction. The manufacturer of that car was like, I'm not gonna give you the ability to touch this thing. I'm just gonna make it work the way that you want it to work. That's the same thing with a stack. I'm not gonna give you the ability to write to the bottom or to the middle of the array that's inside the stack. I'm just going to give you the ability to write at the top. That's going to help you in the future by making it so that you know exactly what kind of data is in here and how to interact with that data. Right? With an array, it's like, I don't know, I can add or remove from anywhere. With a stack, you know you can only add and remove to me. So push is just going to push. Pop, it's just going to pop. Holy cow, that's so far so good. It looks like pop also removes from the end, right? Oh my god, so that's amazing. Okay, so what does peak do? How does peak implemented? So what peak is it just gets you the thing that you're going to pop, right? And since you always pop from the end, then what peak does is it just says, go to the last, return the element at the last index. And the last index is array.length and so on. Make sense? So that's it, that's the implementation. Is empty just converts length to 0, and then here is the implementation. So this class right here is a stack that has a push, it has a pop, it has a peak, and it has an isEmpty, and it works. So they're simple to conceptualize in code, and yeah, that's not how you spell exercise. Cool. All right, so I want you to do these things. Implement a stack using linked lists. You may not use array or built-in array methods. You implement the linked list based stack with the following methods. So it's the same method we've seen before. All right, so you're all going to do it. Before we get started, though, does everyone know what a linked list is? That's a wild question. Should I teach that? I shouldn't teach it.
Oh yeah,
So I shouldn't do this exercise?
we can do the exercise with the array.
But no, the exercise is implemented using linked lists. Do you want me to teach linked lists real quick?
I don't think that's actually possible.
Oh, it's not possible? Okay, we're just
The exercise is that given a string, add it to the stack, the stack implementation that you just made. So have a string with maybe your name and add it to the stack. And then after that, we see what happens when you pop. See what happens when you
Yeah, just play with this implementation. Let's take 5 minutes. Let's say 24. We're going to go to 8:20. We're going to go to 8:30. Copy paste this implementation into your editor or to your like JavaScript interpreter, and then I want you to push onto this stack your name 1 character at a time. So basically, have a string my name equals quote Ben whatever, and then push each character 1 at a time, and then pop and see what happens.
So it's like something like this. The class name, the class name. Right. So I was thinking split it. And then I was gonna implement it. Okay. But then I think finish that and change it back at the end. Yeah. But of course, after that, then we can have different functions. If I'm not mistaken. Yeah. Okay. This creates the instance. So you have that. We'll put it in there. Then we should be able to use any of the methods that was in the last slide. None of that popped up. So copy this, copy this, copy this. Yeah. Yeah. Okay, so maybe we do have to, maybe here. We can, you declared it before, right? Yeah. So maybe, yeah, because it's gonna have to be a slate because it shows up, it's gonna show up. See if that works. Nope. I got some cool things. It's kind of important. It's still on the file.
Everybody down? You still working on it? It worked, right? What did it do? What did you see? Which is the which letter? Is it the last letter?
Yeah, like I put the first one and then the third one and then I saw the
Wait, what do you mean the first one and the third one? What?
like the first letter of the string.
Oh, so you only push like some random letters. You didn't do a for loop? You should do a for loop. You should take some long string, like your full name, like Benjamin Louis Herschel Sussman, like name equals, quote, BNJMIN space LULIS space HIRCHUFALE dash SSIN, that's my name, small. And then put that in quotes. I want you to push every single character into the stack, and then I want you to pop it. Tell me what you see.
That's
Okay, alright, here we go. Think about it. Okay. So what? Okay. So this is the variable, that's the new instance of the class. I don't even know. Let's just so I have a name up there as I'm sure, but let's just see what happens. So maybe not. Should probably just name. So I had name first as an set as an integer. Then for the instance, my name is new instance of set. Has name. So now I'm pushing in the first name. Yes. Also a string, since name is a string also. And I also log it out and give it. So hopefully that'll work. I don't know. Let's try the next one. That sounded good. Okay, yeah, here we go. Now push the max thing in. I feel like it is, but I don't know. I guess I'll just have to figure it out. Because if we just make the string, and it should just.
go. All right. So this is I implemented it, so you can take a look at it. So here's the stack. I just pasted it in from the site. So here's my name. It's really long. You'll see how long it is by looking at it. I made a stack. Looks like it's a new stack. Let's put something on. I loop through my name, and I push each character of my name into the stack. Then, while the stack is not empty, I pop off the stack. What do you think it's going to print out? What do you think it's going to print out? My name backwards. Let's see if that's what it does. Oh yeah, my name backwards, right? So it's last in, first out. So the last thing in was this N. It's the first one out. Then the next last thing was A. The absolute first thing that went in was this B, right? That's the first thing that went in, character 0. And that's the last one to come out, right? So first in, last out, and last in, first out are the exact same thing. We always say last in, first out for some reason, but if someone ever says first in, last out, they're not wrong. But they're the same. But last in, last out, and first out, those are not the same. Okay, any questions on this? See how I printed it out backwards? Does this make sense to you? Do you have a question? Do you have a comment? Do you have a concern? Do you have any emotions at all? Share them with me now. Please. How do you feel? You feel okay? You need more position. What's up?
I mean, I don't know, it's about a little bit about the WoW movement.
Yeah, go ahead.
Seem to be running it all. This,
Did it what?
it's not going to run, right?
It just ran. Look at it.
I mean, yeah, that ran, but well, it's not empty, so the console not on.
Yeah.
That's okay. That's
Wait,
good.
This is, well, it's not empty, right?
No,
There's something in the stack popping. So this is a very common stack-like looking thing.
Yeah.
While it's not empty, pop. Right? It kind of reads the way that you think it's like. Hey, if this thing is not empty, pop. Keep doing that until it's empty. As soon as it's empty, stop popping.
And the array is not empty, but it
The
is.
stack is empty.
Second.
The array there is no array. This is a string to begin with. The question of the headphones.
How did it come out, man?
How the hell did it come out backwards? Okay, so let's walk through it together. Let's just do a much shorter name. Just bet, okay? All right. So I want you to tell me, plaid shirt headphones. Okay, we've got a stack, right? And maybe you've got your like pencil and paper right there. So I want you to draw like on your sheet. Draw a line. Draw a line. And that is a stack. Everything above it is going to be like that's the table, right? You're going to put a stack of plates on it, okay? And there's nothing there yet because you haven't put a stack of plates. So let I equals 0, I is less than the name dot length, I plus 1. So starting at 0, go all the way to the end of the name, right? So what is I the first time that this runs? What is I? I is B. I is 0. And names of I is B. Okay, you're a little bit ahead. I is 0. Names of 0. Name of 0 is B. So I'm pushing B. So why don't you write B? Put B on your stack. Right? So imagine like you have a table, you have a bunch of plates. And you have a plate, you write B on it and put it on the table. Okay? Now what's the next value for I? 1, right? So the name of 1 is E. So then write E, put it on top of the stack, above the B, right? Okay? What's the next value of I? 2. What's name of 2? Okay, so write N. Okay? What's the next value of I?
3.
Okay, 3. Is 3 less than name dot length?
Yes.
No. Name dot length, the name is only 3. Well, sorry, I made my name shorter for the interest of, so we don't, this isn't taken out. My name is really long. I'm doing the short version of my name. So is 3 less than name dot length? No. What's name dot length? Is 3 less than 3? No, right? So we don't push anything on stack. So look at your stack. What do you see on it? What's at the bottom of the stack? B's at the bottom. What's in the middle? What's at the top? If I were to peek, what would I get? Okay, sweet. If I were to pop, what would I get? And then if I popped after that, what would I get next? And then after that, what would I get next? And after that, what would I get? Fail, actually. You can't pop an empty. You'd be like, error. Right? Actually, what happens when I pop? Let's see. Let's do this. While true. Let's see what happens. Oh god, undefined. So it actually doesn't fail because JavaScript is really robust. It pops undefined forever. But yeah, so you get undefined. Okay, so the first thing you got back when you popped it was n. So that's why it's backwards. First thing you pop is n. Second thing you pop is e. Third thing you pop is b. Does that answer your question?
Yeah.
Cool. Thank you. Yeah, my pleasure. Good question. Question on the side.
Would you possibly do it with
I don't think I can do it quickly. I can show you what a linked list kind of looks like. So like what a linked list looks like is it's like, so you have like a node, and what a node has on it, is it has like a value. And you know, it's like, let's see, it's like a constructor or whatever. And it has like some value. What is it? So this on it. Let's say it's undefined at first or whatever. And this dot next is also undefined. And maybe actually the constructor should have a value. So this is what a node looks like. A node is a container that contains some value and a pointer to the next node, a reference to the next node. And so then you can make like a linked list by linking these nodes together. So you can be like let n1 equal to new node of 10, right? That's the first one. And then we can be like let, and then not let, n1 dot next node is equal to new node 11. And then we can be like n1 dot next node next node is equal to 12. This is a linked list with 3 elements, 10, 11, 12. You know that you're at the end of the linked list when you look at the next node and you see is it undefined. If next node is undefined, you're at the end. So think about it like an array, it's an ordered list, but you can't go to like, you know how you can do an array of 10 instantly? You go to the 10th element right away. You can't do that with a linked list. You have to follow the next node, and then follow the next node, follow the next node, follow the next node, follow the next node. So you'll wrap these nodes together and you'll have like some linked list class, right? Class linked list. I'm doing this really fast. This isn't part of the class. Although presumably you will learn this soon. So you know, it'll spoil it from some main class. So basically what a linked list class is going to have, it's going to maybe have, it's going to be like this dot head node. Define this dot and this is and then you're going to have like an add method. This is just a method. It's like add, and it's going to take a value. And what add's going to do is it's going to be like, all right, if this dot head node is undefined, or really probably just do if it's false. Let's do that. If it's false, then we're going to make a new node. So we're going to be like this head node is equal to new node value. And then we're also going to say this tail node is equal to this head node. So basically, the thing at the front and the thing at the back are both pointing to the same node, right? And else, if it's not, like if head node is, or this should be like this, else meaning there is a tail node, this dot tail node dot next node is equal to new And then basically, oh yeah, then we also want to say this dot tail node is equal to this dot tail node. And I'm going kind of quickly, but like this is way, way easier to see when drawn out. I feel like we have a lot of time, so I'm just going to go for it. Okay, so this is, can I run this? Is that okay? Let me make sure that it erases before I go. Oh yeah, there's writing already on there. Yeah, it's fine right on this. Why are you laughing at me? Shit. Okay, so think about a linked list like this. Right? So this little box here, what is that? This little box is up here, what is it? It's, what do you call it? It's a word up there. This dot. Yeah. Speak up. This dot. No. There's many of them. There's one here, there's one here, there's one here. What is it? It's this dot. Head node? No. Wrong. Next node. Right? This is a node right here. Right? It's going to have a value. It's going to have a next node. Maybe I'll draw this even bigger so I can really, you can really see it. This is, I'm drawing too small, aren't I? Here, I'll go over here, and I can draw really big. Okay, so we're going to make a node. Here's a node. It's going to have a value, right? So, and then it's going to have a next node. Okay? Here's some other guy. It's also going to have a value. It's also going to have a next node. Here's some other node. Oh my God, guess what this is going to have? Someone tell me what's going to have? Value. And a next node. If I want this to be the last node in my linked list, what should the value of the next node be? Undefined. We're gonna draw undefined with an X. It's a very common standard thing. So here is a linked list. How many elements are in this linked list? What would be the runtime of an n-element linked list to get the value of the last node? Kelly, good job. Did everybody hear that? This is a throwback to the first class or the second class or whatever it was. So what's the big O runtime to get the value of the last element of an array? Over 1, right? Arrays of constant time access of arbitrary element. But it's O of n to a linked list. That kind of sucks. Why would you ever use a linked list? Array is a billion times better. It's n times better, right? Who can tell me, why would I use a linked list? What situations might a linked list be a superior solution? Think about it. Think about it. Did you think about it? Did you think about it? Anyway, talk amongst yourselves. Talk amongst yourselves. Talk to your neighbor. What do you think would be a situation? Now we know that array has better performance, right? It's got better performance. Why would I ever want to use this freaking linked list? Talk to your neighbor. What do they think? Over an hour. We have over an hour and 20 minutes left. We have over an hour and 20 minutes left, so we have a lot of time. Let's do another 15 minutes then for the queues. The last hour. We did stacks. That's what I'm using.
Should see everybody. It will go through until you reach the
Okay, here I hear the room dying down a little bit. Who has any ideas? Give me your ideas. There's no bad answers. That's something. There are some bad answers, but they're probably not that bad. What's up? A music player? Okay, I love the answer, but I need to understand it. Let's elaborate. 1 second. Tell me why the music player is good. Don't read it from the internet. Tell me what you're thinking.
Press the forward and the back button to like scroll through songs and stuff.
Okay. Why is that better than an array, though?
I have no idea.
It doesn't sound better than an array. An array you can go forward and back pretty easily, right?
I would assume you have like your playlist and genres you go into each one.
There's no fixed value.
There's no fixed value? I'm not following. What are you saying?
With an array,
I like these ideas, but I'm not understanding them. Let's talk about them a little bit.
with an array, you can, C# is probably one has an array out of opposites.
Yeah.
With the list, I can keep adding on. So I can
I see. So you're using the C array definition, where an array in C is a fixed size. But I'm using the JavaScript array definition. A JavaScript array you can push on. It's not a fixed size. Array can mean different things in different contexts. You're probably reading some Google article that's like from C or something.
No, I actually program C#.
Well, you program C#. Okay. Right. But and C# has a linked list concept. It also has an array list concept. The JavaScript array is actually an array list. But I'm still looking for this answer. Why would I use a linked list?
I think blockchain is
Blockchain is a linked list. That's true. But I don't like that answer because blockchain is stupid. I should think that answer over here.
So I'm going to say I have no answer for you, but maybe if you ran through that example again, maybe we can come up with a new
Right.
idea.
Which example?
Just run through how it works again. It's really quick.
Okay, so this is the linked list, right? It has a head and a tail pointer. That's just to keep track of where everything is. If I want to get like element 3 of an array, I just go to the third element and it works. If I want to get element 3 of this linked list, actually there's only 3 elements, so there's, let's say element 2 of this linked list. Right? What I would do is I would follow the head and I would say, okay, this is element 0. Then I would follow the next node, this is element 1. Then I would follow the next node, this is element 2, I found it. That operation took linear time.
And
Right.
you can't go through the tail to get that.
I could have gone through the tail, but I don't know. Yeah, I could have gone through the tail. And probably we have a length here, let's be honest. We often have a length. Because it's usually just very useful to have a length. And then you can be smart. You can be like, oh, if the length is like 100, and I want to get 99, then it's like, great, I just go to the last one over there. Right? If the length's 100, I want to get 50, then I have to go either 50 in from the left or 50 in from the right. It's going to take 50 hops, right? I have to follow this node 50 times. So what do we think here? An encrypted password. Why would a linked list be better for that?
Because an array is useless to jump to any other character besides the first
Why that doesn't sound useless to me? It sounds awesome. Oftentimes in encryption, you want to like take subsets, right? You want to like say, like, or take the top 32 bits of each character and create a new byte out of that, and like, so you oftentimes for encryption you want to have constant access. So I'm gonna go with the hard no on that one, but I like where you're going with your head. What's up in the back? Okay, everybody hear what he said? Say it louder. This is the right answer. What? Come on!
I got it, man. I'm gonna say it right now.
Okay.
Say an item, you could instead of item, you know, those two things easily. One in an array is tough.
Did everybody hear that? I want you to think about that for a second before I explain it. Just let it absorb into your head. I'll repeat it so that you can hear it from my mouth. When you want to insert an item into an array, think about you have an array of 100, right? And I want to insert something in the middle. What's involved to insert something in the middle of an array? And what would be involved to insert something in the middle of a list? Just think about it for a second. Just think about it. How would you do it? Question over here.
I think for like an array, if you wanted to insert something, you would have to be like change the index of each every item after or before.
So imagine if I have an array like this, ABC, XYZ, exclamation mark, right? If I want to insert something between C and X, I want to insert D. How do I do that? I have to add a new element here and move the exclamation mark. Then I need to move the Z. Then I need to move the Y. Then I need to move the X. Then I can insert the D. How long did that take? How long did that take?
So you think there's no way for an array to magically just move things out the way?
No, it's not magical. The reason why the array has constant time access is like, hey, I want to get element 7,000 of this array. Gives it to you right away. The reason why that is because this array is actually contiguous memory in your machine. You remember we talked about this? Random access memory. Have you heard of the Daft Punk record? Random access memories. That's a reference on the thing in your computer right now. Everyone in front of you, you've got a computer with gigabytes of RAM in it. Right? Am I talking crazy? Okay, you've got RAM in your computer, right? RAM stands for random access memory. What that means is it is constant time to access any random bit of memory. That's literally what it means. That's why it has the word random in it, is because it's fast to access a random thing. And it doesn't mean it's fast to access a random thing as in like, hey, roll the dice, I'll give you a thing. It means, hey, any random ass thing that you want, I'll get it. You just have to tell me what index it is. And so arrays inside the computer are actually continuous memory. So this is like a physical thing. Like on your computer, there's a physical RAM chip. It looks like this. It's got little pins on the bottom. And there's little like black cubes. I'll show you a picture of it. Looks like that.
That's old.
That's RAM.
Look at that.
That's
RAM.
Right, so this is RAM. So you can see, like, see how these, like, all of these, like, pins? So what this is your computer can say, hey, I want RAM address 774537422745. And it'll be like, blam, 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 it's over in this thing, it's over in that section, boom, I got it. And it knows that because the hardware is built to have constant time random access. That's like, it's built for that purpose, okay? So if it's built for that purpose, if you want to insert something in the middle, you can't like open up a portal in space-time and like just move things over, right? They're physically sitting there next to each other on RAM. So you need to actually move each bit over one at a time, right? Until you have space and then you can insert. That takes linear time. Question?
So for like the node, all you have to do is just change the next node value and the other node value.
Right. In order to do it for a node, let's say I want to insert something in the middle here. I make a new node. Some value. Some next node. I make the next node point to the previous next node, and I make this one point like that. Boom, boom. I make a new node. I point the node that I want it to be after to it, and I point the new node that I made to what this used to be pointing to. And that's it. Now suddenly, this is in between those two. And I didn't have to move this one. This one is sitting in RAM somewhere. But it could be, the thing is that this could be at RAM address 10, 500, 4, 7 billion. It could be anywhere. Because when I see this next node, it's a pointer. It's telling me, okay, go find this thing. It's a constant time. This pointer is just saying some address in RAM. Right? And so the way that it actually works, this is like if you were learning C, where you'd be like teaching you how this shit actually works. Is an array in C is not an array. There's no such thing as an array in C. An array in C is actually just a pointer to the first element, and then you just add. You like pointer to the first element plus 1, 2, 3, 4, 5. That's why it's zero indexing is that's why the first element is 0, is because in C, an array is just a pointer to the root of the array. When you add 0 to it, you get the first element because it's right at the head. You add 1 to it, you get the second element. Crazy, right? Anyway, you don't need to learn C. I'm not teaching you C right now, so don't worry if that was over your head. But what shouldn't be over your head is fundamentally why an array is actually not that good of a data structure is because adding stuff to the front of it, anything other than adding to the end, is pretty shit. Because if you add to the front, you have to shift everything over. So it's actually linear time to insert to the front. It's not linear time to insert to the front of an array in JavaScript, because JavaScript arrays are actually called array lists, which is a different thing. I'm not going to teach you what it is because it's complicated. But it's a neat combination of these two that is the performance characteristics of both. Anyway, this is a linked list. This is an array. Linked list has linear time search. Array has constant time search. Linked list has constant time insert. Array has linear time insert. Shit. Okay, question.
So you're saying that last node right there didn't change its element name or anything like that? It's still the same?
So the thing is that you'll notice that in this example down here, I'm not naming any elements. Like this new node doesn't get a name. I'm just putting it as the value to this field on this object.
For this position, is it even a number or?
Right. So the position of an element inside of this is relative. Right. So this position used to be position 2, right? 0, 1, 2. But after this insert, it's now position 3.
And why is that exactly different than the positions of an array?
It's exactly the same position.
So how is it any better?
It's better because the runtime of this insert operation is constant, whereas the runtime of this insert operation is linear, which is significant.
Well, the same, it's just the way it's being done is different.
Hell yeah.
Okay.
That is the fundamental data structures and algorithm. That's how data structures and algorithms work. Remember that that's why this question was like, hey, look, we can implement it using arrays, or we can implement it using linked lists. It's the same thing, just two implementations. You can make a stack both ways. In fact, a stack is much, much better as a linked list than an array. Why? Why is that? You had a question? Yeah.
Like, if let's say when it's something in the linked list, don't you have to search quickly the list? Or would that be end?
That's a really good point. If you want to insert into the middle of a linked list, you have to search to get to the index that you want. That's correct. So, which operations are constant time? Inserting at the front, inserting at the back. Those are constant. Inserting in the middle will be linear because you have to search through. It's true. So I think inserting at the front is probably the most interesting because in an array, when you insert at the front, it's actually linear time, so you have to shift everything over. When you insert in a linked list, it's constant for sure. But yeah, absolutely right. If you want to insert into the very middle, it's actually linear time for both. So that's why the array list is really nice. Because what the array list does is instead of having a single value here, it has an array here, and it has some length here. And so then what you can do is you can be like, all right, imagine that this array has like 100 elements. So I could be like, oh, if I have this like linked list of size 1,000, it actually only has 10 nodes in it. 10 nodes each with 100 elements. But they can have different numbers because I could remove one and say, well, now this one's 99. And I can add one, and this one has 101. And so they usually have buffer space, and then when they hit some limit, they split into two. And when they get to some small limit, they merge together. So that's what the array list is. It's a very complicated data structure. Just kind of that's like how JavaScript gets the like performance that you see, which is like, oh yeah, it's really fast to insert in the front, and it's really fast to look up an element or random index. It uses features of both. But yes, it's linear time to insert in the middle, but it's constant time to insert in the front. This is linear time to insert anywhere. Okay? Let's look at the implementation one last time before we go over to queues. So here's my implementation over here. When I add a value, I say if there's no tail node, so under what circumstances would there be no tail node? Well, under what circumstances would there be no tail node? When there's only one, is that correct? When there's only 0, right? If there's 1, it will be a tail node. The tail node and the head node will be the same, right? As you'll see here, look, the tail node and the head node are the same, right? They'll point to the same one. We'll be like, oh yeah, that's it, there's 1 element. When there's 0 elements, there'll be no tail node and no head node. In this implementation, linked list can be implemented in a lot of ways. Otherwise, there exists some nodes. So we're going to add it to the end. So we're going to say, the tail node's next is this new node that I made, and now our tail node points to the new node, which is what it said next. Right? We could have done it like this. We could have said like, it's the same. That's the same code. It's a little bit more readable. Right? Where basically I make the new node that you want to make, and then I put it as the next node for the current tail, and I update the tail to be pointing to that. Who wants to together add a, let's do like a remove end, remove last. Who wants to walk me through how would I implement a remove last? Let's do it together, shall we? I'm going to remove the last element of the linked list. How do I do it? How do I do it? Front row. Let's go. Use your pipes. Get some volume. Back in here. What should I type?
This dot.
This dot what? Actually, remove last kind of sucks. Let's do remove first. Remove last actually really hard. I'm doing it much easier. Remove first is much easier. Remove first. I want to remove the first element. Okay? Feel free to talk amongst yourselves. How would you implement this? Talk amongst yourself. How are you going to implement remove first? We're gonna come back to the front row, folks. But maybe y'all can help them out. Talk amongst yourselves. How are you going to implement remove first?
But you don't want to go to the tail node and then go backwards. That would take.
What type of value?
That would be limited on. That's what it takes.
So it's a nice job script. Is that value to be three numbers, two strings? It could be an object. It could be another language.
Do they? Do they? I think so.
Alright, front row.
Because link linked lists, they don't have indexes right now.
I can't hear you.
I said linked lists don't have indexes like the arrays would, so you can't necessarily.
I mean, they actually do have indexes. Yeah, the index is in the eye of the beholder. I choose to say that the first one is index 0, the second one is index 1. That's just, I just choose to say it. You can't use that square bracket notation, but I can say, hey, index 0 is that first one. And I'm trying to remove the one at index 0. How do I do it?
I figured that you would do this dot zero and then the value of the first.
So what that would do,
So,
But then,
well, no, what I'm hearing you say, this dot tail node dot value equals this dot tail node parentheses. So if I do this dot tail node parentheses, that means tail node is a function. Tail node is not a function. It's an object, right? It's a node. So what I want to do, right? How do I know what? Like, look at that linked list up there. See the box's linked list. How do I know what's the first element? This is what?
the head, the first element will
The
be
head. That's the answer. The head, right? So when I remove something, what have I done? Like when I remove something, what am I actually doing in this context?
because the head is going to go to that one, so it will go to the next one.
Yeah.
Yes, that's exactly right. You make, instead of the head pointing where it's pointing now, it should point to the next one. So if I say this dot head and I get the second one, I did it. So how do I write that down? It's easy, I promise. It's easy. There's no tricks.
It should go to this dot head node dot next node. That would go to the second one.
Exactly. So let's write it all down in our heads.
So,
Let's write it down. Let's start writing it down. So you said like this dot head node, right? Right?
this is the first, and the next one will be dot next node.
Right? Okay, so that's the second element that we want to be the new first element, right? So we're
So
moving
then this value, shouldn't this value then be assigned to what you define as the
No, who knows what this value is? Because this could be a million elements in this already, right? What we want to do though, remember, you say what you said again, because you said it really correct.
Yeah, basically, what it wanted to go to the first one is to change the head instead of being linked to the second.
To change the head. How do you change the head? What do you write to change the head?
So with that head, they'll just have
this dot
Okay, say it aloud, really loud.
So this dot
Okay, front row got it. Beat you to it. Good job, front row. Okay, what are we gonna write? How did you remove first? It's coming back up, I promise.
we said this dot head this dot head node to this dot head dot next node.
Please.
It makes the first one, which is this dot head node, be equal to the second.
You got it. I want you to tell me. All right, ready. Remove first. How do I remove first?
So you would type this dot head node is equal to this dot head node dot next node. No. Was it? Yeah.
Okay, so to explain this, lady in the front row is going to say how she came up with it. Ready, go. Wait, listen to the front row. Listen to the front row.
So basically, what you're trying to do is change the direction from the head going to the first node to the second node. So when you do that, you target the head node, and then that's when you make it this dot head node is equal to the next node.
Good job. All right. So it looks simple. So it looks like a really simple line, but there's a lot going on in this line. Right? There's a lot going on in this line. What this line is saying is it's saying, what I want is I want head to point to this, right? what removing the front of a linked list means having the head no longer point to the current head, but instead of the head point to the thing that was after the head, the next node of the current head. And so the only way to get to this thing is this, like head node dot next node. Okay, now I've got this, right? Head node dot next node is the thing that I want to be the new head. So I need to update head to be that value. That's exactly what we're doing. This dot head node is now going to be the previous head node's next node. Right? We could even write this just to make it really clear. We could be like const previous head node is equal to this dot head node. Right? And then we could be like previous head node dot next node. And maybe we could even be like const new head node. This is just me being really pedantic, just to make it super clear. And then we could be like this dot head node equals new head. So this is the exact same thing written really long, right? Because this variable is just this dot head node. So this dot head node dot next node. And new head node, I just put it in head. So anyway, this is, I don't know if that was helpful. That might have actually been really confusing. I'm not doing it. Sometimes people like verbose names like that. Anyway, okay, cool. Question in front.
Quick question. So let's say you have nodes of 1, 2, 3, and use this code to change the head node from 1 to 2. Would it be just 2 to 3, or would it be 2 to 3?
2 and 3. Right? Basically, this is pop.
Okay.
Right? And this is push, although it pushes to the tail. So let's have it push to the head right now. It's not head node. There's no head node.
You say
Then we can just screw the tail node. Tail nodes are dead to us. Okay, so I just implemented a stack using this. I just did it. Okay? What does it have? It has pop and it has push. Oh, yeah, we usually just give it peak, right? Let's do peak. This is going to be return this head node. Oh, and this should also, pop should, pop should return the value of the right? So now, so basically this is now, we don't need a tail node. The tail node is really useful for like a full-on linked list, and there's actually a thing called a doubly linked list, and then there's a doubly linked list with a sentinel. I'm not going to explain any of that shit to you right now, but this is a stack. It's not called a linked list, it's called a stack. Because what does it have? It has push, right? And what push says is, if there's no head node, we just make it, right? Otherwise, that means there is a head node. We make a new node. We say that the new node's next node is the previous head, right? And now we say the new head is that new node. And then when we pop, we already wrote pop. Pop was the front row of pop, right? But the one thing I added was we need to get the old head's value, right? Before we remove it, we need to get its value, and then we return it because when you pop, you want to return, right? And then peak just says like, yeah, we'll get the head. So you want to talk about this push real quick? We talk about that. Yeah.
Sorry, it's like the next node is kind of bothering me. Like, where is that method coming from? Did you make it, or was it already something
No,
that?
there's no next node method. Where do you
That's
see
not
it?
a method. No, what is what do you call it? It's there.
Where? Which line?
That next node. Line 21.
Yeah, nodes have next nodes. Let's see, nodes have next nodes.
Okay, sorry. I didn't say
Right here.
Right, no, I just thought like your
Because that's the only thing.
that was the only thing there. Okay.
That's Nodes only have two things: a value and next node.
Gotcha.
Right? Those are just two fields on this object.
Yeah.
Right? Is that what you're?
No, I forgot that class was.
Right. So that's what we're referring to here. This is just a node class, and then here's my stack class. The stack class starts with an undefined head node. So when I push, let's walk through the push operation. Right? So let me get this erase here. So the push operation says. Here's my stack. 1, 2, 3 elements, right? So I want to push something onto it. Well, I have access to the previous head, right? So what I want to do is I want to make a new node. So I make a new node. And I put the value in it. And it has a next node, because everybody has a next node. And where do I want this next node to point? To the old head, right? I want it to point like that. Because I want to make sure that when I remove it, this becomes the new head, right? It's like a stack. It's like when I put something on top of the stack, I want to put it on top of the old head, the old top. Right? When I'm putting something on the stack, what am I doing? I'm actually just saying there used to be a top, and I'm putting a new top. And then now that's the new top. And then I put a new top on top of that. And then I put a new top on top of that, right? Each time I'm putting a new top. So this is the top. Calling it head. And we make a new node. We say this new node, its next node is the old head. So it's this dot head, new node dot next node equals this dot head. And then I update head to point to map. That's what I do. So there's 3 steps here. I make a new node. I set its next node to be the old head. And I set head to be this new node. And this is a stack and when using linked lists. We done did it. Okay, now we're going to do queues. It went a little longer than I thought. Okay, we're going to do queues. Ready, set, go. Queues. Web. We did it. Okay. Should we take a break? We didn't take a break, did we?
Yeah.
Let's take a break. Let's take a 5-minute break. Everybody go for a little walk. If you have any questions, I'm up here and we'll go to what's up?
Oh my God.
Are you talking about push or pop? Pop. So yeah, pop gets deleted. Yeah, once it's orphaned. Well, I mean, it's complicated. The reality is that it actually does exist, but the garbage collector will eventually clean it up. But it's orphaned. So like, see how we've got this pointer here, right? So it's like, if we want to get to this node, we follow this, we follow that, we follow this, we found. But what if I wanted to remove this? All I would do is I would just then it's gone, right? This still exists. But how do I get to it? And so the computer, JavaScript will see like, oh shit, nothing twice in this. And it will eventually, that's called garbage. It kind of does. It kind of doesn't. It does stick around, and eventually the garbage collector will clean it up. So it's this. This is kind of a big idea. Garbage. Oh. Right, so we can look at garbage collection jobs. We can see memory management is performed automatically. We create objects. So the main concept is reachability. So reachable values are those which are accessible users of Connect and sort of. So global variables are reachable. Variables from other functions are reachable. Global variables are reachable. And etc. Those are groups. So like basically if you have a variable like var, foo, or let foo, whatever, it's a root. Any other values report if it's reachable from a root by a reference. So these arrows are references, right? So it's easy to and then it's to a reference, to a reference, to a reference, to a reference. So generally what architects will do is they'll do reference count. So it's like, so here it is. Here's a global object, John. So here's like user is an object with name, John. And then we say user is equal to null. Now suddenly, look, object John, there's no pointer here. We used to have a pointer for user. We will get garbage color. So that's how that works. It's not instant. It might take, it could take 10, 20, 30 seconds. It could take hours. You know what I mean? Chrome is, let's see how much memory my Chrome is using. Holy shit. 2.4 gigs of RAM. What the so that thing. What was it? What was doing? It's crazy, right? Did I just free up to force quit it? That too. Smart. This is like frequently there's like so much great things about this. But yeah, basically, you'll often see like this with all of this. There's so much RAM, and that's because it's not very good content. And it's also because JavaScript is not very good content. And that's just a feature. This is the reality of working in a weakly type reference language. It's a great question. What? Oh no, I I'll write it out again. Wait, what did you want me to write out? So like this class. So first they wrote this, and then it was like you wanted to do like push or something. Was it push? So push a value. There's this like if this dot head doesn't exist, then else. That, right? C is a sticky language. JavaScript is made to be a lot easier, but also it means it's a lot more. It's a lot easier to fuck up. C it's a lot harder to fuck up. I mean, this is the most C thing ever was. Linked lists are like the most C thing in the entire system. If you only learn one thing in C, it should be like this is the same. This is how you implement it in C. Like I can figure out how to implement C. It was just like this. Okay, we just have to use struct instead of class. There's a class. C sharp. You can have a but C sharp. Classes are data structures. Structs are data structures. Structs are not classes. They'll look like it's a fixed size, basically a collection of fields. Fixed size. Class is like a collection of fields Usually a variable size operations models. That's why I use our classes. Okay, we are going to do cues. Let's go. All right. So we talked about philo, right? First in, last out. Right? You remember the example of the elevator, the example of the juice, the example of the airplane. Those are the things that the first thing that went in is the last thing to leave. What are some examples where the first thing in is the first thing to leave? Tunnel, right? If you're driving in a tunnel, you're the first car to get in. You're going to be the first car to get out. What else?
Printing, when you're printing a whole bunch of files, first thing and second print.
When you're printing, that's a great example, right? And especially if you make a big queue of print jobs. I want to print this, I want to print that, I want to print this. Wow, it's going to take a long time. It's going to print the last one last. What's another example?
When you're in line ordering food.
When you're waiting in line ordering food, or waiting in line to do literally anything, waiting in line to get on an airplane, waiting in line to get off an airplane, whatever it is. The first person to get in line is going to be the first person to get in the food. What's up?
Gravity.
Gravity? Explain that one, okay.
Alright, so Alright, let me try to
Go on.
About this first, and about this second.
Oh, I see. Basically, I see.
Yeah.
So,
I would
the
think
first thing
that
you drop will land before the second thing you drop. That is What are some other examples? You don't have any examples of first in, first out? Come on, you gotta have one. Can't think of anything in the world that's first in, first out? Think of something. Come on, be creative. Oh my god. This is your chance to help us. Yes? No. What are you laughing at?
You just have to say thought.
What was that thought? Like,
Go ahead,
go ahead.
Well, if you put your shoe on the right foot first, then you take it off first. But it was weird that we had to
That is a
say
weird
it on.
example.
That's why we're laughing, because it was the exact same thing.
Thanks for sharing. Okay, you've got more time to think about it. Do you have one yet? Traffic. Definitely, right? At the traffic light, first person up to the stoplight is the first person to drive away. Good example. See that one's okay, so that's first in, first out. I think the waiting in line at food is going to be the example that I'm going to use like for the rest of this conversation because it's just kind of an easy thing to talk about. Everyone does it. Everybody waits in line. Everybody literally queues up at a Shake Shack. Okay, cool. Another example would be like text messages. If I send you 10 text messages, first one that you're going to receive is the first one I send.
Sometimes. Not all the time.
You know what?
It's an Android.
Waiting in line at the DMV. Manager calls it a help desk. Ordering and a fast food restaurant. Okay, so these are all kinds of things. Okay. So when you add a new element, it goes to the end of the queue. When you remove an element, you remove from the front of the queue, right? When someone arrives at the restaurant, when they arrive at Shake Shack, they don't go right to the front of the line. That would be mean, disrespectful. You don't do it, right? You go to the back of the line, and you wait like all the others, right? And when someone is like, hey, the cashier is ready to let someone order, they don't grab someone from the back of the line. That would be so disrespectful to people that are waiting so long for their tasty burgers. Instead, they do the person in the front, okay? First in, first in, okay? Bye. Okay, so it sounds a lot like a stack, except the big difference between a stack is that you add to the top of the stack and you remove from the top of the stack. You add to the back of the queue and you remove from the front of the queue. Right, that's basically it. Okay, so NQ is the name, so you know we have push and pop. We have NQ and DQ. They're like basically the same thing, but they're different words because they mean something different in the context of the stage structure. So NQ is when you add someone to the queue. Guess you add someone, you add them to the back. DQ means you remove from the queue. Guess you DQ from the front. Okay? So just like in stacks, queues are only allowed to access the next element in line to be DQ'd. Like if you were to peek on a queue, you would get the first in line. You would not get the last in line. So remember how we talked about if you peek, pop, you'll get different stuff. But if you peek NQ, peek NQ, peek NQ, what happens? So remember how earlier we were talking about on a stack, if you peek, and then you pop, and then you peek, you get something different. What if you peek NQ, peek NQ?
The last, you show the last thing you had, right?
What do you think happens?
So it was peak and
It's going to go to the next one. I don't understand.
show this.
Peek, remember what peeking is? What is peeking? You see the what element? Which element do you see? Yep, NQ is like literally think about it, you're at Shake Shack and you have a line of people. And someone shows up and they're like, what should I do? I've never been to Shake Shack before. And you say NQ. I'm serious. And then you know what I mean? Like it's like you're at the next City Field, right? And there's a huge fucking line of people waiting to get in through security. And some rando shows up and is like, what do I do? And you're a security guard. And you're like, NQ, right? And then another person shows up, NQ. What are you doing? You're putting them where? At the back of the line. And then you're the security guard that's like, okay, I've got space. I can scan you now. DQ. Who are you grabbing? Front of the line, right? So if I peek at the front of the line, I see who's next. Then I NQ. Then I peek again. What happens? What do I see? Different person? New person? Same person?
It's the same person.
What do you think? What do you think, Rachel? Woman in the gray shirt behind the man in the gray shirt. Oh, you're all wearing gray shirts because it's the pursuit shirt. Oh my god. That's not helpful. What do you think? You gonna see the
next one.
I don't understand the next one. What is the next one? If you're at Shake Shack and you're like, show me the next one, what does that mean? Is it the person in front of the line? Is the person in the back of the line? Use words relative to the line. Okay?
Yeah.
You're standing in line at Shake Shack, right? You're a cashier at Shake Shack. You're like, okay, next one to get an order, right? You look to see who the next one is. Who is it? It's me. Okay? Somebody shows up to NQ. You look to see who's at the front of the line now. Is it someone different or is it the same person?
Same person.
It's the same person. So if I peek NQ, peek, it's going to be the same. And that's really different than pop, right? Pop, or rather, or push. Push is actually better example. Pop is more like DQ. When we push, if we were to peek, push, peek, push, peek, push, every time we peek, we'd see a new value, right? But if we were to peek NQ, peek NQ, peek NQ, every time we peek, we'd see the same value. You understand that? Okay? There's not a trick here. This is just like understanding how lines work in Shake Shack. If you understand how a line works in Shake Shack, you understand this. I'm just trying to give words to this, right? So I want to hear the next one. I want to hear NQ and DQ. I want to hear front. I want to hear back. Okay? Okay. Okay. What did I do this time? Okay, cool. So Ray, Brian, Sam, and Mike, without a K, are are in line. Ray's at front, Mike is at the back. If I DQ Ray, Brian becomes the front. If I NQ Vicky, Brian is still front, but now Vicky is the back. Okay? It's just a line at Shake Shack. Okay? So whenever you hear Q, I want you to think it's a line at Shake Shack. Okay? Is everybody Shake Shack? It's a line. It's a line. I don't know. Maybe you haven't been there. You haven't been to Shake Shack. Okay. What's your favorite restaurant?
In England, they call lines Q's. Yeah, so look at that.
This guy speaks British. Are you watching the Drag Race UK? Are you gonna watch Drag Race UK?
I just watched British debates.
British debates. Oh. Stay frosty over there. Sounds interesting. Okay, cool. So, serving people, airplanes, data from a server to a client. It's pretty advanced. Vehicles on a road. Nice. That was yours. Yeah. Okay, here are the methods. NQ value. DQ does not take a value. Why does DQ not take a value? Say what?
That wasn't me, that was me.
Oh, you're a liar.
No, I'm not.
So your mouth moving.
I didn't say anything, no, I was nodding.
You were just like. Okay, you move out. Ventriloquism, go. Let's go, ventriloquism. It's 9:55. Let's do it. Because you're removing the element, right? When you're at Shake Shack and you DQ the person from the line, you don't need to have an input, right? You just look at the line and you say, oh, that's the person in front, right? But when you add something to the line, you gotta add someone to the line, right? Who are you adding? You can't add nothing to the line, you gotta add someone. That's why NQ takes a value. Just like push takes a value, but pop does not. NQ takes a value, DQ does not. Peak is the exact same thing that we thought about. Empty, straightforward. Okay. So, just like the stack, there are several ways that want the queue. For the sake of teaching, we're going to go with the array approach, although we have this cool linked list. And I can show you how to do the cool linked list with a doubly linked linked list at a later date. But we don't have time for that. So we're going to do the array implementation. You can do a linked list. You can do it with a double stack too. I'll leave that for you to think about for later. Once you do the array, I want everyone to think about the double stack implementation. Okay, so here we go. Check it out. Does this look familiar or what?
Yeah.
This is the exact same as a stack. Okay, question?
So like this is basically for both stacks including just like this revolves around making and removing the objects.
Yeah. Yeah, right? I mean, waiting in line at Shake Shops involves waiting and then getting food and then leaving, right? It's like, what do you do when you go to Shake Shack? You show up, you wait in line, you move forward slowly in line until you're in the front, then you order your food, and you leave. Oh, there's a little bit of waiting. What's up? He said mobile pickup. What is this? Uber Eats? Bullshit. Bullshit. I don't pay for that shit.
Well, if you think about it, if you are building Uber Eats, then that application will need a queue because the pre-orders before me.
Yeah. So NASA shirt is trying to be snarky, but actually, he's blowing his own mind with the fact that he's like, in real life, I can stand in line in a queue, or I could go online and insert my order into a queue. It's funny because it's true. But no, seriously, it's true. Okay, so this is very familiar. You okay? You hurt yourself. With that humor, okay? Don't hurt yourself. All right, this looks familiar because the backing data structure, the underlying data structure that stores the information for a stack was an array in that example. The same will be true here. We are going to use an array. And if you remember, push in the stack case was just array.push. Pop in the stack case was just array.pop. But that's not going to work here, right? Because if we push and pop again, we're going to get first in, last out. We get FILO. We don't want FILO. We want FIFO. So talk amongst yourselves. How are we going to do it? Think about the stack implementation. In fact, maybe bring up the stack implementation from the previous guide. Look at it and think, how can I change this to give me first in, last out as opposed to first in, first out? Or, no, first in, first out as opposed to first in, last out. Basically, how can I get a queue instead of a stack? Okay, and I'm going to bring it up so we can all look at it together. Here it is, right? Everybody see this? So look at that, talk amongst yourselves. How would you change this to make it a queue? Let's go. Okay, I want white shirt over here, white blouse. I'm going to call you next. Get ready, just get prepared. No, you're the only one with the white blouse. Oh no. I just want to prepare you emotionally to get ready, okay? Talk amongst yourselves, get some hints.
With the push rights, besides the name to be
Yes. Yeah. That's where
But the push is NQ, right? NQ is
so we get the value. That's why.
So push, we just change it to the method and a self-part. And then P, we have to get it.
But
P goes to the first one, so that will give them all. Yeah, it should be first and then but then that's what it is. This
Yeah, it could be.
and then the return value is this. Oh, first. First index is a number, is 0. So we can then just do the find the index number, separate at first index, which is already finished.
Okay, let's bring it back, let's bring it back, let's bring it back. So here's what I did is I copied over this, the stack implementation. Go back over to here. I copied it over, I renamed push to be NQ and pop to be DQ, okay? But this implementation is broken, right? This implementation is not first in, first out. It's first in, last out, right? Because when I push, the most recent thing that I push will get popped. So how can I change it? What do you think? Actually, no. I'm going to this one right here. Sorry. Say again. Change pop to dot shift. What does that do? Let's find out. Always just, just run it down, Google it, and I put WD Schools because it's a really good place. Remove the first item. Oh my God, how convenient that there's a method that is exactly what we want. And that's it, end of list. Oh wait, no, but this is wrong, right? Peak is also wrong. How should we change peak? Don't look around, get your hands down. It's all you, I believe me. Let's look at what shift does, right? What does shift do? Read that out loud to me. No, seriously, just read out loud. It's going to help you. It's going to help out. Okay, so shift is going to remove first item of the array. So DQ is going to remove the first item of the array. Sounds good, right? Peak should return what DQ will return next, right? Peak is like, oh shit, I don't have any space. I don't have any, we're out of burgers. So I'm not going to take someone out of the line and give them an order. But I want to see who's the unlucky SOB who's not going to get ordered. Right? And I'm going to peak. So I need to see the next person that would have gotten DQ. Is it the person at the last index of the array? Which index of the array is the person that's going to get DQ next? We index 0. So I can just whammo. That's great, right? So this thing works. Let's prove that it works. Let's say like, what do we need to do? We need to say like, oh, we call it stack. We should call it queue. Let's do const Shake Shack. Queue. So we're gonna be like Shake Shack.execute. What's your name? Madeline? Catlin? Kathy.
With the K.
Oh my. Right?
Yeah, that's right.
It's a close one, but I got it. Kathy, she gets the front line. And then I'm going to go next because I am very hungry. And then let's DQ somebody else. Manejo? Sure. I can't hear what anybody's saying. It's loud. You're not loud enough. Okay, and then let's say like while Shake Shack. Remember that's all Shake Shack. That is empty. Well, it's not empty. Right? Let's console. .log d Shake Shack. Shake Shack. Let's go. Let's see. should work. That'll work. Okay, Kathy comes first, then Ben, then my name. Do you want me to change it to someone else's name?
Vallejo.
Vallejo.
I'm an instructor.
Yeah, so maybe that makes more sense. Sorry, I could have sworn you were saying Vallejo. It's a little town called Vallejo. No, I'm not going to. I get distracted easy, you can tell. Okay, Vallejo, that makes more sense. He's going to get his burger last, I think. So Kathy gets first, then me, then Vallejo. This is exactly what we expect. Cool, it worked, right. What did we do? We made it shift instead of pop. And we made it 0 instead of, let's make sure that the peak, it's a peak here. So this should be, cool, right? So that's it. That's a queue. You did it. You done did it, folks. Okay, we did it, we did it, we did it, we did it. 0, it's empty, put it all together. Okay, everybody using linked lists, well, we kind of already did that.
So, just like everything in this class, this will require practice, right? We're going to get to see more in detail what the linked list is and how to use it. And the most important thing that you can go home with from this class is the idea of having a queue and a stack, like just the idea, not even, we're going to get to look in more detail as to the implementation and the methods, but how we could, there's something that I've been saying in this class over and over again. The entire purpose of programming languages is to represent the real world in a computer so that we have the computer do stuff for us. So we saw how we can represent the dog in the computer, right? Where a dog has a breed and a name. We saw how we can represent an island. This is the same thing. We're just representing a real world queue and a real world stack. And that comes with some benefits. So thank you, Ben, for the lecture. Don't forget to come in Saturday at 9:45. And that's it. Thank you.
We finished that.